Can you believe it? The spiders we see everywhere are actually one of the most underestimated top-tier killing machines on Earth. They do not have explosive sprinting speed. They do not have hard armor protecting their bodies. They do not have a bright, toxic-looking appearance. Their brains are even only about the size of a poppy seed. And yet, this tiny creature has almost single-handedly suppressed the evolution of the entire insect world. Even highly lethal wasps do not dare approach web-building spiders carelessly. Even flying insects 3 to 5 times larger than them are almost doomed once they crash into their traps. Even more outrageous is this. As long as spiders appear in an area, the entire local insect ecosystem can fall into panic. So why can a spider with such low intelligence crush insects that can fly, run, and fight back? What kind of unbelievable black technology is hidden inside its body? Today, we are going to completely break down the spider's all-around, overpowered survival system. First, let's correct a common misconception. Spiders are not insects at all. Since childhood, we have casually grouped them together with bugs. But in reality, spiders belong to Arachnida, a completely separate class from insects. And it is precisely this difference that gives them abilities insects simply do not have. The first one is a real-life spider sense. Many people look at a spider's 8 eyes and assume it hunts mainly by sight. That is another big misunderstanding. Most spiders have very poor vision. Many species can barely see clear images. Their hunting does not rely on carefully watching with their eyes. Instead, their 8 legs are covered with thousands of extremely fine specialized hairs, known as trichobothria. The sensitivity of the sensory system may completely overturn your understanding from several meters away. Even the faint air disturbance caused by a tiny flying insect flapping its wings can be detected with precision. In addition, slit sensilla on the surface of the spider's body can sense the weight of dew, the direction of a breeze, and accurately distinguish different vibration frequencies. The movement of leaves in the wind, the panic trembling of a fly, and the smooth gliding of a moth are completely different signals to a spider. And the web it spins is an even more powerful extension of its nervous system. It is like a giant hearing net covering an entire area. Prey may avoid visual tracking, but it cannot hide the slightest movement. Before it even reacts, its location has already been completely exposed. Of course, perception alone is not enough. The second core reason spiders are so powerful is their unique body-driving mechanism. Most animals on Earth, including humans and insects, move through antagonistic muscles. One group of muscles contracts, while another group relaxes. The movement is stable, but it has physical limits. It is not only slower, but also creates friction and sound. But the spider's body structure jumps completely outside this rule. Its legs have flexor muscles, but no true extensor muscles. Its movement and lunging depend on high-pressure hydraulic force from hemolymph inside its body. When it needs to strike, the pressure of its body fluid rises instantly. High-pressure fluid rushes into the limbs and violently extends the legs. This is why spiders often walk in a jerky, strange way. They are not simply walking. They are using pulses of body fluid to drive their limbs. This overpowered mechanism gives them incredible explosive force. They can go from complete stillness to full speed in an instant. And throughout the whole process, there is no muscle friction and no joint noise. Their attack is silent. Even if an insect is on full alert, it cannot hear the spider approaching. This also answers a classic question. Why do spiders curl up after they die? The answer is simple. Once a life ends, the hydraulic pressure inside the body disappears completely. Without extensor muscles, the limbs can only contract inward. That creates the curled up posture we commonly see, with perception and speed already in place. The spider's ultimate weapon is still its web. Many people think a spider web is just an ordinary sticky net. That is completely wrong. From an engineering perspective, spider silk is one of nature's top mechanical materials. A single spider can precisely produce 7 types of silk with different molecular structures. Some are used to build the web's framework. Some are used to wrap prey. Some are used to protect eggs. Some are used as aerial safety lines for escape. Among them, the silk used specifically for hunting directly outperforms steel in several key ways. Imagine this: if an airplane crashed at high speed into a giant steel net, there would only be 2 outcomes. Either the steel cables would snap, or the aircraft would be torn apart. But spider silk achieves a perfect balance between strength and elasticity. When a fast-flying insect crashes into the web, the silk does not resist rigidly until it breaks. Instead, through changes in its molecular structure, it absorbs and disperses the prey's impact energy layer by layer. It uses the prey's own collision force to slow it down and lock it in place. On top of that, the special biological glue on the surface of the silk does not freeze in low temperatures and does not fail in dry conditions. It can firmly wrap around the tiny hairs on an insect's body, creating full surface adhesion. No matter how agile a flying insect is, once it hits the web, it loses its ability to resist within 3 seconds. There is basically no escape. Under normal circumstances, the trapped insect is still alive. It should still have a chance. But the spider's way of eating completely breaks the defensive logic of most creatures. Ordinary predators need to bite, chew, and swallow their prey. But spiders evolved an extremely efficient form of external digestion. The moment a spider bites its prey, it injects venom that already has digestive functions. This venom can directly break down the prey's muscles, organs, and nervous tissue from the inside. It turns the entire insect into liquid nutrition. Then the spider only needs to suck up the fluid nutrients. The empty insect shell can simply be thrown away. This strategy is almost impossible to counter. The insect's hard outer shell becomes useless. No matter how strong the body is, it collapses from within. That is why spiders can easily prey on creatures several times larger than themselves. Of course, not all spiders rely on webs and wait passively for prey. There is an even more terrifying type. Jumping spiders. They take intelligent hunting to the extreme. They possess logical thinking abilities that are extremely rare among invertebrates. Their vision is also near the ceiling of the arthropod world. 4 pairs of eyes give them panoramic vision. Their main eyes are comparable to telephoto lenses. They not only form clear images, but can also see ultraviolet light that humans cannot detect. The most outrageous part is their hunting intelligence. When prey is in a blind spot and cannot be reached directly, a jumping spider does not rush blindly. Instead, it actively plans a route. It moves through complex terrain, circles around to the prey's side or above it, and launches a precise ambush. Inside its tiny brain, it can build an environmental map, lock onto the prey's position, and accurately calculate a jumping path dozens of times longer than its own body. In a natural world where most microcreatures rely mainly on instinctive reactions, the spider's ability to think and plan is almost like a dimensional strike. At this point, many people may ask if spiders have maxed out combat power, perception, intelligence, and equipment. Why have they not wiped insects out completely? The answer is very real. Almost all the defensive abilities insects have today were forced out by spiders. This has been a two-way evolutionary arms race lasting hundreds of millions of years. Insects evolved hard shells to resist spider bites. They evolved unpredictable flight paths to avoid web interception. Some moths developed shock, absorbing scales to reduce flight vibrations, specifically to hide from the spider's sensory radar. Some flies and ants even imitate the body shape and movements of spiders, disguising themselves as similar creatures to confuse predators, and sometimes even fool spiders themselves. There are also insects that have figured out the structure of spider webs and specifically walk along the non-sticky areas to secretly steal the spider's prey. Almost all the insect features we see today evolved step by step in response to spider hunting. You could say that the entire evolutionary history of insects is also a history of escaping spiders. In nature, every creature has its counter, and nature always maintains an exquisite balance. It is precisely because spiders exist that insect populations are kept firmly under control. You can hardly imagine how important spiders are to Earth's ecosystem. It is no exaggeration to say that if all spiders on Earth suddenly disappeared, human civilization would face a major disaster. Without spiders suppressing them, insect populations would explode in a short time. Agricultural pests would spread wildly. In just a few weeks, fields could suffer devastating crop failure. Mosquitoes, flies, and poisonous insects would spread across the world. All kinds of infectious diseases would spread rapidly. The human living environment would deteriorate sharply. The reason we can live relatively peacefully and the reason crops can grow normally is largely because spiders are silently keeping insect outbreaks in check. So here's a question. If the spider's body structure is so close to perfect, why did its hunting system never evolve giant spiders that could threaten human survival? Because Earth's physical laws have completely locked their body size limit. The first limit is oxygen supply. Spiders do not have lungs like mammals. They rely on book lungs and gas diffusion to absorb oxygen. This system is only suitable for small bodies. Once the body becomes too large, oxygen cannot be delivered effectively to the internal organs. A giant spider would simply suffocate from lack of oxygen. The second limit is skeletal support. External skeletons follow the square cube law. As body size increases, body weight grows much faster than the load-bearing capacity of the outer shell. If a spider grew to the size of a dog, the moment it activated its hydraulic limbs, its legs would bend, crack, or collapse. It would not be able to survive. This perfect hunting system is destined to work only at the centimeter scale. Although their size is limited, spiders have already pushed their survival abilities beyond almost every boundary. Land alone is no longer enough for them. Diving spiders can use silk to build underwater air chambers, storing air and creating underwater nests. They can live in water for long periods, hunting small fish, tadpoles, and aquatic insects. And the spiders can not only go underwater, they can even take to the sky. They climb to high places, release special ballooning silk, and use atmospheric static electricity and wind to travel through the air. Humans have discovered spiders drifting in the wind at altitudes of 5,000 meters, even over the open ocean far from land. Apart from Antarctica, spiders can be found in almost every corner of the world. In soil, in water, in the air, and inside human homes, they are true all-terrain survival kings. After watching this video, I believe you will never underestimate tiny spiders again. Of course, in daily life at home, there's no need to panic. You only need to be cautious of highly venomous species such as black widows. The vast majority of spiders are beneficial creatures that silently help us eliminate pests.